So we want to discuss a third example of first order ODE. The equation is described over here. dy dt equals y over 2 minus 3/2 of y square. It's a nonlinear autonomous differential equation, and it's defined such that y is positive, and there's an initial condition given that y of 0 is some number y0, which must be a positive number. So that's the definition of the equation. And what we want to do, as we have done before, is that before we solve the problem in detail, we want to get a qualitative feel. We want to get a sense of what the solution is going to look like and anticipate the outcome. And so that qualitative picture we want to get. And so there are two steps, as we have said, in getting this qualitative picture. We first solve for the equilibrium solutions, y sub e. And remember, the equilibrium solutions are the solutions for which the differential equation gives us a zero slope or zero right hand side. So the right hand side function f of yt, which is this function for the present problem, we put it equal to 0, and we can then solve for y, which satisfies this equation. And we can see, we can simply factor it, and we can see that it has two solutions, ye equal to 0 and ye equals 1/3. So we have two roots to the equilibrium solution, and we're going to plot it in the overall plot to anticipate the behavior. And so the next thing we need to do is to sketch the direction field, because that tells us the direction in which the trajectory of the solution will evolve from any position in the yt plane. And so we go to this yt plane. The vertical axis is y-axis, horizontal axis is t-axis, and we had discussed a solution like this before, and I've sort of borrowed the same representation here, but the values have changed here. The horizontal axis, remember, is now going from 0 to 1 and larger numbers, and the vertical axis has been zoomed out. This value here is 1/3 and 2/3 and so on. So we draw the equilibrium solutions, y equal to 0 here and y equals 1/3 by these dotted blue lines. Those are the equilibrium solutions. And then at every point we evaluate the slope, and we draw that as an arrow in this plot. And so this is something which is relatively straightforward to generate, because the slope field here is only a function of y. So we can consider different levels of y and evaluate this and correspondingly draw numbers. And we can see that when y is equal to 1/3, then this right hand side vanishes, which is something we have anticipated from the equilibrium solution. And so the change in the direction of the arrows follows from the anticipation that the vectors are horizontal over here. And so that's the overall vector field of the slope. And so starting at any point, the solution is going to evolve such that the slope of the curve must point in the same direction as the local vector field or local direction field that we have. And so starting from here, if we follow the arrows, you can see that it's going to go in this direction, but then the slope of the arrows reduces, and so the slope of the curve is going to reduce, and then asymptotically it will approach this value of 1/3 if we start from below. And likewise, we can anticipate that if we start up above, it's going to approach towards 1/3 from up above, and ultimately the value for long times is going to become 1/3. So given this global picture of the arrows, we can see that regardless of where we start in this upper half plane with respect to value of initial condition, it will ultimately go towards the value of 1/3. That's the nature of the solution, and the time scale over which is going to change to the value 1/3 is something that depends on the coefficients in the problem, and so for that we have to solve the problem in detail. So that's the next step that we will do. So we want to now talk about another example of first order differential equation, but we want to now consider a nonlinear problem which will extend from what we have talked about before. So here is a particular equation, a differential equation defined here, dy dt equals y over 2 minus 3/2 y square. Clearly we can see the nonlinearity here. So as we saw by graphing the equilibrium solutions and the direction field, we have a sense of the nature of the solutions of this equation, but we can motivate those solutions in another way. So if we look at this equation and think about y being small, then this term will be negligible, and so this equation is the equation of boom and bust that we talked about, and so it will be an equation of boom with the positive 1/2 here. So solution would grow, but as solution grows, then y square will no longer be smaller, negligible, so this will become appreciable, and when it becomes appreciable it will change sign, because when y becomes big enough it will dominate, and so then the slope will become negative, and so the solution will grow, but then the growth will be prevented, and so it will go to an equilibrium, as we saw from the qualitative discussion. So to completely define the problem, let's say that nonlinear differential equation is autonomous, no time on the right hand side, and is defined for y being positive. This kind of problem arises in population biology or logistic equation and so on, and so y represents the population density and it's a positive number, and some initial condition is given that at t equal to 0 there is some value, and that of course is also a positive number. So that defines the mathematical problem, and now we're going to illustrate a particular solution methods for it. So the method we want to illustrate is the method which is based on separating variables. The independent and dependent variables are separated, and we want to show that this method applies to this nonlinear problem also. So here is the original equation, and we have simply written the right hand side in a factored form because this will be useful later. And so this depends on y here, and t is just in the time derivative, and so we can rearrange this equation in this form, writing dy over y times 1 minus a third equals minus 3/2 times dt. And so now we have separated y from t on the two sides of the equation, and so we have the equation in separated form, and so at this stage we can say that let's integrate the equation and proceed from there. So that's the next step. So with the separated equation, we want to integrate this equation. The left hand side of the equation is nonlinear, and so the question is, how do we integrate this equation? We can't integrate it as simply as we had in the previous example, and so we need to recall the idea of partial fractions, which I'm sure you learned about in high school algebra. So for example, this quantity which is appearing in the left hand side of the equation, 1 over y times y minus a third, can be expressed in terms of its partial fractions. So some unknown numerator a over y plus some unknown numerator b over y minus a third, and then simply doing the cross multiplication and so on and equating that to this, you can find that these factors a and b are equal to minus a 3 and a plus a 3. And so we can find that the partial fractions are this, and once we know the partial fractions, we can rewrite the original equation in this form. This is the first factor, and this is the second factor, and this is the right hand side minus 3/2 of dt. And so at this stage we can see that each term has a factor of 3 showing up in the numerator, so we can simply divide the equation by 3 and get rid of this factor of 3, and then here we have minus dy over y, which can be integrated as minus log of y, natural log of y, and here we have dy over y minus 3, and so that integrates to log of mod of y minus a third. Reason I didn't put mod over here is because we know that y is positive, and so we don't have to bother to write mod here, it's already positive, but this number could be positive or negative, and so we put the mod sign here, and integrating this we'll have 3, remember, got dropped from the equation, and so integral of dt minus dt over 2 is t over 2, and then plus some arbitrary constant c1. And so at this stage the left hand side can be just rearranged. We have got 2 logs, so that can be written as log of this expression divided by y, that's equal to this expression, and so now the left hand side is purely a log, and so we can get rid of the log by taking exponential of both sides, and so therefore mod of y minus a third equals y on the other side times exponential of this factor, which is exponential of c1 times exponential of minus t over 2. And so we have this expression, and then what we have to do is rearrange it a little bit and then impose initial conditions. And so that's the equation that we had, and we want to impose initial condition on it. The initial condition is that y is equal to y0 at t equal to t equal to 0. So we put y0 here, and when we put 0 here in the exponential, we have exponential of 0, which is equal to 1. And so this equation is simply an equation for c. We can say that c is equal to y0 minus a third divided by y0, this expression. And we can then substitute this expression back in the original equation. And so that's the solution now in terms of the initial condition. And this equation right now has y appearing on both sides, but y appears linearly on the right hand side. So we can simply take this factor of y out and solve for y explicitly. And so that gives this expression, which in a clean form I put in a box. And it's in a form where we can interpret it very nicely. So for example, we can see that when t is equal to 0, then this exponential of minus 0 will be equal to 1. And so this prefactor here is going to vanish, and this factor is going to become 1. And so y will be equal to y0 at t equal to 0. And then as t increases, for large times, this exponential factor will become negligible. So we can drop that. And in here, this factor will become negligible, and so this will get dropped, and so then we'll have y0 over 3y0, so y0 will drop. So regardless of the initial condition, as time increases, y will go to 1/3. That's the equilibrium solution that all initial conditions are attracted to in this particular problem. And so that is something that this solution exhibits, and is something we had anticipated from the qualitative nature of the problem. So that closes the discussion of this problem.